Good afternoon, everybody. It's time to get started again. Welcome back to day 2 of the Symposium on Computing for the Common Good, sponsored by the College of Information and Computer Sciences, or CICS, at the University of Massachusetts, Amherst. My name is Brant Chaikas, and I'm the Executive Director of the Center for Data Science. During this afternoon's session, CICS faculty members will present short research talks on current research in core areas of data science. Topics will span data privacy, computer vision, causal inference, cognitive neuroscience, graphical data processing, information retrieval, and natural language processing. Now, as we've noted before, this is a Zoom webinar, so for all attendees, their microphones and video cameras will be disabled. But we do want to encourage as much interactivity during this session as possible. So to submit questions at any time for any of our speakers today, please use the Zoom Q&A feature. Just tap on the Q&A button at the bottom of your Zoom screen. A window will open and you can type in your question. After each research talk, we'll have a very brief moment for the speaker to answer one or perhaps two questions. We have a very tight time schedule, so we're going to move things along as quickly as we can. However, at the very end of the session, after all the talks are completed, there will be an optional separate Zoom session where anyone in the audience who'd like to interact live and have an actual conversation with any of today's speakers can go and do that. And I'll have more to say about that at the end of today's session. All of today's talks are going to be recorded, and they are all going to be made available to you after today's event, so you can see things that you may have missed, share them with colleagues, and so forth. I just want to take a moment to provide a shout out and thanks to our devoted and outstandingly wonderful ASL interpreters, Laura and Jamie. Take a bow. And we also have Jessica, I think I've gotten her name right, who's doing live captioning. So in fact, if you haven't used live captioning in Zoom, you should see a button at the bottom that says live transcript, and you can click on that and turn on the live captioning. So we have both ASL and live captioning going on throughout this session. Now, with that preamble, let me introduce our first speaker. Jerome Miklow is a professor in CICS, and he's a leader in the DREAM Lab. The DREAM Lab stands for Data Systems Research for Exploration, Analytics, and Modeling. He's also part of the Cybersecurity Institute. Today, Jerome is going to speak on fair decision-making using privacy-protected data. Over to you, Jerome.
Today, I'd like to describe some recent work on fairness issues that arise in the context of privacy-protected data. My work focuses on the challenge of protecting sensitive data, which I define as personal information whose misuse could cause harm. The typical scenario we consider is shown here. Respondents contribute their personal data and expect privacy protection. They trust the data curator to collect data and handle it responsibly. In particular, the curator governs the release of data or derived data products to analysts who want the most accurate insights to properties of the respondent population. Analysts may be well-intentioned, but we nevertheless consider them untrusted, in part because they often expect to publicize findings derived from the sensitive data. For this reason, we'd like to restrict the analyst to only seeing privacy-safe results. For example, if we use Uber, we become respondents because we have an account with Uber, and Uber collects and stores detailed records about our trip. The city of Boston would like to study aggregate trends in this data, for example, to inform policy decisions. If Uber releases data to the city of Boston, it must ensure that individual activities cannot be recovered from the data. In this talk, I'll focus on another example, data collected by the Census Bureau. In this case, respondents are US residents completing their census forms. The Census Bureau needs to ensure individual privacy while publicly releasing sets of aggregate tabulations, which are widely used by social scientists, demographers, and policymakers. Privacy technology operates at the boundary between the curator and analyst, balancing the need to protect the individual with the need to share with the analyst accurate aggregate trends about the population of respondents. Many legacy privacy technologies have been shown to be vulnerable to subtle attacks, resulting in a series of high-profile exposures of sensitive personal data. In fact, the Census Bureau attacked some of its own 2010 data releases and found easy-to-execute attacks against a large fraction of the US population. In response to these threats, differential privacy has emerged as the leading model for privacy protection. It provides a rigorous, quantifiable privacy guarantee that can encourage participation by respondents. For the curators of sensitive data, it provides a uniquely reliable measure of privacy loss, allowing them to transform data and share it, confident that it will not be attacked and lead to unintended disclosures. Lastly, the privacy protection provided does not rely on the secrecy of the methods employed, which supports algorithmic transparency. The Census Bureau has adopted differential privacy to protect data collected as part of the 2020 census. As someone who's done years of research into differentially private algorithms, this was an exciting moment, and I was lucky to work as an advisor to the Census Bureau, helping them design their algorithms. But as I learned about the uses of privacy protected data at the census, I was also motivated to study the potential impacts of privacy protection. So while I feel that the adoption of differential privacy at the Census Bureau is a major step forward, we also have to be aware of the potential consequences of privacy protection in the important applications that census data is used for. In particular, disparities in treatment that could arise for certain groups. To explain this further, let's dive into the census example in a bit more detail. The Census Bureau collects information from residents and generates tables of population statistics. Generally, these population statistics count the size of demographically and geographically defined groups. Examples of population statistics include the number of senior citizens in a county, the number of school-age children in each school district, the number of voting age residents speaking a given foreign language in each voting district in the US. To protect privacy, the Census Bureau has always applied disclosure limitation methods to the statistics before releasing them publicly. To protect privacy, the statistics are transformed or distorted in some way, and therefore inaccuracies in the statistics are introduced. When differential privacy is used, we randomly perturb the statistics, adding random samples of noise to each statistic generally. Census data are used for all manner of important decisions. So we've studied a class of problems we call assignment problems, in which groups of people are assigned a resource or benefit using an assignment rule defined in terms of published population statistics. For example, approximately $6 billion of education funding is distributed to school districts in the US in proportion to the population of low-income school-age children in each district. Those population counts of children in each district determine the allocation of funds. Another really important assignment problem, the number of foreign language speakers in a voting jurisdiction is tested against a population threshold to determine whether ballots will be printed in a foreign language. Inaccuracy in public statistics has serious consequences for affected groups. They may receive less funding than they rightfully deserve, or even suffer disenfranchised voters because their district is misclassified. But we have to accept some degree of inaccuracy if we want to protect privacy. A central question of our work, however, is whether affected groups bear equally the burden the burden of inaccuracy introduced by our privacy mechanisms. We performed an empirical study of these assignment disparities in the context of differential privacy. We considered 3 important assignment problems, tested both standard differentially private mechanisms and some more sophisticated ones, and we used public use census data, which was treated as ground truth for the purposes of our simulations. The noise added by common differentially private algorithms resulted in significant disparities, especially at stronger levels of privacy, which entail more noise. For example, in the assignment of educational funds, we witnessed inflation of allocations to smaller districts by a factor of 10 or more, and a compensating reduction in funding to larger districts. In the case of voting rights benefits, which involve classifying districts as deserving or not deserving of voting materials published in so-called minority languages, we witnessed large disparities in the rate of correct classification. Some districts are largely immune to noise and retain their benefits with high likelihood, while others end up incorrectly classified more than half the time. The Census Bureau is required to make an important social choice, balancing privacy against the accuracy of the public statistics it releases. Because this is such a high stakes trade-off, it's very important to have the most efficient privacy algorithms, and much research is focused on designing sophisticated algorithms that offer better accuracy for a fixed level of privacy. But one of the key takeaways from our work is that accuracy measures commonly used in the privacy community need to be expanded. The research community often targets aggregate accuracy, implicitly favoring a utilitarian goal. This would correlate to minimizing the total amount of funding that is misallocated. We could instead pursue a more egalitarian goal of making sure no group is impacted too badly. What can we do to remedy the disparities we witnessed? Notice that the public population statistics are typically used in the assignment rule as if they are true values, ignoring the fact that noise has been added. For the assignment of funding and voting rights benefits, we showed that we can mitigate unfairness by changing the assignment rule to account for the noise. This requires knowing something about the noise distribution and knowing that outside the census. But this is an important benefit of differential privacy, that the privacy protection does not rely or depend on the secrecy of the algorithms used. So for the first time, the census will be able to share the algorithms used for disclosure limitation, and it will allow the public the chance to analyze these potential impacts more accurately. And it could allow different assignment rules to be used. For example, for funds allocation, we showed that one can guarantee with high probability that no district is underfunded, essentially by overfunding everyone a little bit to account for the uncertainty in population counts. At a pretty conservative value of epsilon of 0.1, we'd have to increase overall funding by about 8%. These remedies could relieve disparities, but one of the challenges is whether they're feasible in the real world, where assignment rules are often written into law. Thank you. If you'd like to learn more about this problem and related fairness issues, please read our paper, Fair Decision Making Using Privacy Protected Data, and I provided a few other sources that inform the Census Bureau's use of differential privacy.
Very good. Thank you, Jerome. Thank you for that. Come join me back on stage. Turn on your video and audio for a question or two. We have a moment. Hey, so you ended that, of course, with a very intriguing comment about, feasibility in the real world depends on, things being written into law. Could you just, you sort of begged the question. Could you elaborate on that a bit?
Yeah, sure. So what I was proposing at the end there is that it's possible to do some smarter things with the noisy population counts that the census is going to release. But so on the side of the policymakers, they could do a more sophisticated analysis and come up with more sophisticated noise-aware rules for allocating funds or doing these voting rights decisions, making these voting rights decisions. But I think the challenge is that sophisticated analysis is not common. The common approach is just treat the population counts as if they're real and unperturbed. Even though that was never the case at census, there was always some perturbation going on or distortion going on. They were treated as the true counts in policy for the purpose of policy making. So I think that it's both hard and potentially controversial to switch to a model where policy making is done taking into account the mechanisms for privacy protection. But technically, from a statistical point of view, that would be the right thing to do, and we could get better outcomes, more fair outcomes.
Great, thank you. And there's just one quick question. Can you just comment on the availability of these privacy techniques? I mean, of course, they're described in published papers, but are there freely available implementations of them that people could experiment with?
Yes, there's a bunch of, I mean, generally speaking, in differential privacy, there's a growing move to release open source software that carries out differentially private computations. And in the particular case of the census, they're committed to algorithmic transparency for the 2020 census algorithms. They already made a preliminary release of their an early version, a kind of prototype algorithm, which was then, it was open source, it was documented, a bunch of people looked at it, they critiqued it, they gave feedback, in fact, and then the algorithms are being revised, and there will be further publications of those. So ultimately, the algorithms used for the 2020 census, which the data collection happens in 2020, in 2021 is when the data is released, and those algorithms are finalized, they'll be public, and people can play around with them and do more detailed studies like the ones we did.
Great, thank you so much, Jerome, and I'm sorry we had only such a short time together. Great talk. We're going to move on to our next speaker. So let me introduce our next speaker, Erik Learned Miller. Erik Learned Miller is a professor in CICS, and he co-directs the Computer Vision Research Laboratory. Now today, Erik's going to discuss the use of vision in enabling machines to learn from their experience. So over to you, Erik.
Hi, my name is Erik Learned Miller, and I want to talk to you today about something I call learning from experience. This is work with many other people. Many of them were in my lab, and this is a list of the contributors. I won't go through them all. The green ones are UMass folks, including faculty and students, and the others are collaborators from other institutions. So one of my primary motivations for figuring out what problems to work on in artificial intelligence and in computer vision is asking the following questions. What can humans do better than computers? And as computers get better and better and better, and keep adding skills to their list, we can slightly modify the question and say, what can humans still do better than computers? And I think even though computers are getting very impressive at many tasks, there's still a very long list of things we can answer in this question. So one interesting exercise is to sort of think about a brief history of artificial intelligence through the lens of this question. So early in AI, a lot of people focused on the idea that humans can reason logically. And so this led to the development of rule-based systems, logic systems, and strong game-playing systems. After a while, we got tired of programming computers to do the things we wanted, and we noticed that humans can learn from examples, particularly from labeled examples of pictures and things like that. And this led to the development of supervised learning, where we can give the computer, say, 100 pictures of an apple and 100 pictures of a banana, and have it try to learn the difference between these two things. After having done this for a number of years, yeah, I was struck in 2000 when I was a graduate student by the fact that humans can learn from very few examples, even just one example sometimes. And I made my thesis about learning from one examples. This is developed into the sub area of what's called low shot learning. And even more recently, we've been focused on the fact that humans can benefit strongly from exposure to unlabeled data before being exposed to labeled data. So imagine you wanted to learn Spanish, but your class wasn't going to start for 6 weeks. So you decide to listen to the Spanish radio or Mexican radio for 6 weeks, even though you don't understand exactly what they're being said. It turns out this is a big help in preparing you to take a Spanish class. And we're trying to leverage these kinds of ideas in the development of unsupervised and self-supervised learning. So to try to give you a sense of what I'm trying to achieve in the next few years in my lab, let me tell you a little story about the apple farm, a little girl and a robot. So once upon a time, an intelligent robot and a little girl went to work on an apple farm. And neither one of them knew much about apples at the time. The little girl knew that apples were unusually red, or were usually red and round, and she liked the taste of them most of the time. The robot knew how to tell the difference between an apple, a banana, a rhinoceros, and a speedboat because it had been trained on ImageNet, a standard computer vision data set. After 10 years of working on the farm, the little girl's father came to pay her a visit. On the same day, the robot's designer came to see how the robot was doing. The girl's father picked an apple from a tree and said, "What can you tell me about it?" The little girl, who was not so little anymore, smiled and said, "That's a new variety of macoon, but you picked it too soon. It wasn't ripe yet. As you can tell by the fact that the stem came with it, and when you picked it, and that there's a little bit of green near the center on the bottom." She went on for 5 minutes talking about that apple. The robot designer wanted to see how his robot would do. He held the apple in his hand and asked the robot, "What can you tell me about it?" The robot replied, "It's an apple." Now, so what has the robot failed to do here? The robot, despite working on an apple farm for 10 years, has failed to learn from its experience. If it wasn't explicitly instructed to learn something, then it didn't learn it. However, when humans experience prolonged exposure to an environment, they naturally develop expertise, and robots don't. So this is one of the things I'd like to change. And to do that, we have to understand how humans do it and how we can replicate this capability in robots. So I'm going to talk briefly about 3 ways that we've investigated doing this to learn from experience without really being taught explicitly. Okay, let's go on to number 1, which is learning distance, a concept of distance from motion. So we would like our robots and our intelligent agents to be able to answer questions like, how far away do you think an apple is if it looks like this? And how about an apple tree like this? How far away do you think it might be? And of course, we could provide answers to this question. Maybe 1 meter away for the apple and maybe 10 meters for the tree. Now, the question is, or estimating distance from images is a critical human skill, but one which we were never taught. So how did we learn it? And how can robots learn it? Well, a traditional approach might be to teach a robot about distance by learning from labeled examples. And what I mean by that is we give it pictures and a distance associated with those pictures, and we give it millions and millions of these pictures. But this is incredibly tedious because there's so many different objects and so many distances they could be at. So we're going to take a different approach in this work, which is to learn to associate motion and distance. And we published this work in ECCV 2018. So let me tell you a little bit about that. So I'm going to start this with a simple video of looking out the window of a train. Now, as you look out look at this video, you notice that something you already know, of course, that things that are closer to the train go by more quickly, and things that are far away do not appear to be moving much. And of course, you understand this is because of the perspective and the way images fall on your retina. But nevertheless, this is a very simple stimulus, and we want to mine that stimulus to see what we can learn from it, okay? So notice that if we see something that we might recognize, like a tree, this particular tree, by clicking the video, and this tree down here, on the other hand, went by slowly. That is a very simple observation that a computer can make once it's learned how to recognize objects and to track them to estimate their speed. So in this work, we trained a neural network to learn how fast something will move in a video based on what it looks like. So in other words, we can have it try to learn to predict how fast something will go by in the video. And when I show you a big tree like this and say, how fast do you think it's going to go by? You would naturally say quickly, because you can tell it's close. That means you learned a concept of distance and how it relates to the speed at which something goes by. So it turns out that when you train a neural network to predict how quickly something goes by, it naturally separates things into categories based on how far away they are. So that's one example of being able to learn from experience. It's a rich representation that turns out to be an incredibly important part of common sense. So a second project is learning to recognize your own mistakes. So we're going to start with a face detector that's been trained with lots of examples in a traditional way. I'm showing you an example here on the right of an image in which 3 faces have been detected and outlined with these green boxes. But we'd like to make it even better without collecting even more data. And I'm going to show you in a minute that this face detector was making some mistakes. This is work we also published at ECZB 2018. So let's take a look at this video. Now, here we see the output of a face detector, and now here it's going to make a mistake. It thought for a moment that this hand happened to look like a face, and it put a box around it. Now let's watch it make another mistake. It's doing lots of things correctly, but all of a sudden it's going to, for a second, put a red box on the back of his neck, which is of course not a face. And we'll look at one more example here where it's again going to look at his hand as a face. Now you'll notice that when the video does this, when the detector does this, it tends to consistently recognize the faces, but only rarely put a bounding box around something that's not a face. And we call this appearance of a single detection in a sequence of frames a flicker. So the detector kind of flickers on and flickers off. And we've noticed watching these that an isolated detection on one of these flickers in a sequence of video frames is likely to be a false positive, meaning it's probably wrong. So even though the detector doesn't inherently know the difference between these correct faces and this non-face here, which is accidentally identified as a face, we can use the fact that it's sporadic to guess that it's likely to be an error. Similarly, occasionally we'll be recognizing faces in each frame, and there'll be one face that's dropped out that the detector misses. So if we see a sequence of repeated detections with one missing in the middle, we can guess this we call an off flicker, and this is typically a false negative, which means there should have been a detection here. So we can run our detector on thousands of videos without any effort, just by scraping them off the web and running them, and collect these sporadic missing detections and isolated detections, these flickers, and set them aside as examples to retrain our detector. Okay, so just to reiterate, the idea is run the base detector on lots of videos, collect the flickers and label them automatically, and then retrain the detector using the automatically obtained data. This results in substantial improvements in the original detector, and the key point here is that this can simply run on its own and doesn't require any labeling from us. All right. So the third project I want to tell you about is something we've just started, and it's about learning how to represent concepts in a brain-like structure. Often these are called embeddings. And these representations or embeddings should have certain properties. In particular, we want to think about what properties should visual representations have. Well, it seems reasonable that if I see two different pictures of the same thing and I want to come up with a representation for it, that those two pictures of the same thing, two different pictures of the same thing should have very similar representations since they represent the same thing. But pictures of two different things should have more different representations. This seems so obvious that it's hardly worth saying. But how do we achieve that? Well, if I give you two pictures, so I have two pictures of this car taken at slightly different times, and you can see that they're from slightly different angles, so they look a bit different. What I'm saying is, whatever the representation of this car is, I'd like the representation of this to be very, very similar since it's the same car. On the other hand, here are pictures of two different cars. One is the same car as above, and the other one is obviously a different car. And I'd like these representations to be a bit different. So how can I achieve this? Well, a traditional labor-intensive approach would be to collect lots of image pairs that were either same, meaning I have two images of the same object, or different, meaning I have two images of different objects, and train a neural network to make the representations of the same pairs similar while making overall the representations diverse. But here's an automatic way of doing this that's not labor intensive. We can simply get random videos and track random objects in the video and grab different shots of the same object from the tracks of the object. These are guaranteed to be the same object if our tracker works correctly. Then we take pairs of patches or pairs of images from the same object and use those to, we train a neural network to make the representations of those same pairs similar again. So this is a way of doing the same kind of thing, but in a fully automatic way. So so I'm going to show you a very short video here where notice there's a little box on the car here tracking a particular patch. And if I move forward a little bit, I can collect many different views of this car as it moves along and as its appearance is changing fairly substantially as it moves away from us. And I want to train a neural network to continue to make embeddings of these grabbed objects similar because they're the same object, and it should be relatively insensitive to the different views of that object. Okay, so I've talked about three different ways that humans can learn and develop concepts just by watching the world go by, even without teachers. And I'm calling this learning from experience rather than learning from data that's been arduously labeled by a researcher. And I think that as we develop these concepts, we'll be able to train algorithms to have rich new capabilities without having to prepare all the data for them in a very careful way. All right, thank you very much.
Thank you, Erik. Please join me back on stage. And I just want to say, Erik, that you can turn on your video too.
Yeah.
While I was listening to your talk, a robot came up to me and gave me an apple and said something very rude, and that's all on you.
Oh man.
What?
Can you hear me, Brant?
Yeah, I can hear you just fine. Thank you.
I'm struggling with my video.
It's okay.
I'm not sure why it's not on, but I'm happy to answer a question
Okay.
without my video. Sorry about that.
Oh, not a problem. Very good. Well, here's the serious question. So you talked about 3 different kinds of learning from experience that a system could do. You didn't go into much, and understandably so, into the details of each method. But the question is, are you using discrete, 3 different ways of learning from 3 different kinds of experience, or have you observed some kind of generalizable capability across all these different ways? Since, of course, generalizability is kind of the holy grail of all AI work.
That's a great question. I would say, I think you're asking, like, do we have a grand unified theory of unsupervised learning or something like that?
Well, maybe not that extreme.
Well, we're always, trying to generalize what we're doing more and more as we go. And we're looking for techniques that allow us to learn very large numbers of different concepts through the same mechanism. So we still haven't figured out sort of one way to unify all of these, but I do think, for example, that the tracking method that I talked about last could be used to learn good representations for almost any different natural environment. So very, very diverse natural environments. But we're still developing different methods for different skills. So it's just, so that's sort of the holy grail, what you're asking about.
Yeah.
And that's sort of the long-term goal, but it's going to be a while.
All right. Well, thank you very much, Erik. And again, I'm sorry we have to move on. Reminder to the audience that that all of today's speakers are going to be available in a separate session during the break at the end of this whole talk session today. So you get a chance to follow up with Erik.
All right.
So
and I'll try to have my video working by then.
That's right. Very
okay.
Good.
Sorry.
Awesome.
Bye-bye.
Thank you so much, Erik. All right. So let's move on to our next speaker. And our next speaker is David Jensen. David is a professor in CICS. He directs the Knowledge Discovery Lab, and he's also the director of the Computational Social Science Institute, as well as a member of the Cybersecurity Institute. So today, David's going to highlight 3 research projects in his lab on causal models, including explaining why causal models are so important. So over to you, David.
Hello, my name is David Jensen, and I'm going to spend a few minutes telling you about the work of my research group, the Knowledge Discovery Laboratory, and our work on computing for the common good. The Knowledge Discovery Laboratory studies principles, methods, and practices for learning causal models of complicated systems from observational and experimental data. We motivate and evaluate our work by also working on challenging applications, and I'm going to tell you about 3 specific examples. In the first application, we analyzed data about the entire US securities industry and how frequently individual brokers change jobs. Among the things we discovered was that audits conducted by an industry regulatory organization actually caused brokers to leave the firm that was audited, and we were able to show that that was a causal dependence, not just a statistical association. In the second application, we constructed causal models from data about the performance of a database server. We examined performance data on specific queries and identified those parameter settings of the database software that cause specific queries to be processed more or less efficiently. And finally, in the third example, we're currently analyzing data about robotic control systems to explain why the robot takes specific actions and to explain the environmental conditions that cause the robot's navigation to be more or less competent. The laboratory's work focuses on causal models, so it's worth asking why that particular focus. Now, nearly all existing work in machine learning focuses on learning statistical associations rather than causal dependence. However, a wide variety of mission-critical applications require something more than mere associations can provide. Specifically, many applications require one or more of the following. First, many require reasoning about interventions. That is, we want to accurately reason about the effects of explicit actions, rather than just what can be predicted given particular observations. Second, many applications require what we might call robust reasoning. That is, we want to be able to easily adapt existing models to changing environments without having to relearn the entire model. And finally, many applications require some form of explanation. That is, we want to automatically generate human understandable explanations of the model's inferences. All of these three things are obtainable with causal models and nearly impossible with mere statistical associations. Now, I've also mentioned the laboratory focuses on both experimental and observational data. Experiments are usually considered the gold standard for determining cause and effect, so why focus on observational data as well? Well, first, there's a question of feasibility. In many plausible scenarios, experimental data is nearly or completely impossible to obtain. For instance, you can't reasonably expect to conduct randomized controlled trials on the US economy. Second, even when you can run experiments, they're often expensive or costly in other ways. Third, even when you can run experiments, observational data is often plentiful, and it would seem wasteful not to attempt to use that data in some way. And finally, experiments are often artificial in one or more ways, whereas observational data is almost always generated under more realistic conditions. So for all of these reasons, we're interested in analyzing both experimental and observational data. By now, I hope I've convinced you that we're working in an interesting area, but where are we innovating? There have been decades of work in causal inference by highly capable and thoughtful researchers, and of course we're building on that work, but we're doing so in a highly targeted way that we think offers the best chance for major innovations. Specifically, we're focused on developing new principles, methods, and practices to harness previously unexploited structure in observational data that allow us to infer more accurate and more useful causal models. I'll talk about our work in three related areas. First, in how relational and temporal structures can be used to better infer causal models. Second, how procedural structures can help us infer causal models. And finally, how compositional structures can aid causal inference. Now, some of our earliest work in causal inference examined how to use relational and temporal structures to aid causal inference. These sort of structures are common in social networks and organizational data, which often record relationships about, for instance, who works for whom. Software systems, particularly, say, computer networks or distributed systems, also have this kind of structure. And finally, many technological systems, such as data centers or building control systems, have this kind of relational and temporal structures. These sorts of relationships and how they change over time are vital for understanding causal dependencies. However, until our work, very few causal models explicitly represented and learned causal dependencies of this type. We've published a number of key papers in this area, and other researchers have built on that work. Another key finding of our work is that existing formalisms for representing causal models, specifically linear equations and causal graphical models, are overly constraining and cannot easily represent key features of many real causal systems. Recently, we've been exploring how new classes of causal models can be represented by probabilistic programs. These are procedural programming languages with probabilistic semantics and built-in inference methods. Now, these languages are particularly useful because they're substantially more expressive than classical causal models, and they also often provide more flexible and capable inference methods. Again, we've published several papers in this area and several more are on the way. Both of these two papers were published at the International Conference on Probabilistic Programming. Finally, we've recently been exploring how compositional structures can be used to improve causal inference. By compositional structure, we mean knowledge of how multiple objects combine to form other objects. For example, we see this kind of compositional structure in how school districts are composed of schools, and schools are composed of classrooms, and classrooms are composed of students and teachers. Traditionally, in statistics and machine learning, these kinds of compositional structures are sometimes seen as imperfections in the data. However, we show how this kind of compositional structure can be leveraged to make causal inference less biased and more effective. In particular, we use compositional structure to remove latent confounding, one of the most persistent and vexing, frankly, challenges of causal inference. Again, we've published several papers recently on this topic, including a paper at the last summer's International Conference on Machine Learning. I also want to point to some important applications of our more fundamental work that I've mentioned above on how we might apply this kind of work to interesting applications for the common good. Specifically, we've been applying our work on causal inference to two key projects that are aimed at making artificial intelligence models more transparent and more accountable. First, we've been applying our causal modeling work to explain the actions of artificial intelligence agents that have been constructed using deep reinforcement learning. Secondly, we've been doing similar work to assess the conditions under which deep models will be competent, that is, where they will act sensibly, and more importantly, where they won't act sensibly. This work has produced several interesting recent papers, including work at a recent conference on learning representations that critiqued the use of saliency maps in reinforcement learning. Saliency maps are a common method that purports to explain the inferences of deep models, but we show that much of that purported utility of saliency maps evaporates when they're rigorously tested. Finally, we're also working on a more overarching project to upgrade the way that the community evaluates its own research progress. Evaluation in causal inference is substantially more difficult than it is in conventional machine learning, because evaluating a causal model requires knowledge of the effects of intervention and can't be easily evaluated with a simple holdout test. Specifically, our analysis has shown that existing evaluation methods are often unrealistic in several ways, and we've suggested and developed several more realistic and more effective ways to evaluate new and existing methods for inferring causal models. We've published, of course, several recent papers on this topic, and these papers are already having an impact on how others in the field are evaluating their newest systems. Thanks for your attention, and please feel free to contact me if you have questions about our work.
All right, thank you, David. Thank you for that. Join me, please, back on the virtual stage for a question or two. I don't have an apple for you, but I do have another question for you. This is a variant of the question that was asked earlier of Jerome, which is, are there freely available implementations of these inference algorithms? And really a question, sort of a flip side question about your sense of their maturity for application, right? You know, are they ready to handle really large data sets that our industry partners might be dealing with and so forth?
So, two answers to that. Certainly, one answer is that there is software out there and lots of standard implementations of a variety of algorithms. Another answer is that, like many things in machine learning, it is best to apply those standard algorithms with somebody with fairly advanced training behind them. And so there are a set of kind of very reasonably deep problems that you need to think about with a specific data set. And so you want somebody with experience in causal inference. And I will say that, you know, there's been applications of this work for 30 years with varying and improved methods over that period. It's not like it's a new thing, but all along during that period, it's taken people who can work closely with domain experts to tease out some of the assumptions and understandings that are necessary to underpin a good analysis.
Great. So a great argument to work with your friendly neighborhood flagship research university when applying this kind of work.
Yeah, unfortunately, it's not a sort of you know, shrink wrapped, pull it out of the box, pour the data in, and get causal inference out the other side.
All right, but a great advance over mere statistical association.
Yes.
Very good. Thank you so much. People will be able to chat with you after the session is over, and we're going to move on to our next speaker. Again, thank you, David. So our next speaker is Hava Siegelmann. Now, Hava Siegelmann is a professor here in CICS, and she directs the BINDS lab, BINDS, which stands for the Biologically Inspired Neural and Dynamical Systems Laboratory. Now, Hava recently returned to our college from time she spent at DARPA, the Defense Advanced Research Projects Agency, where she served as a program manager. And for that service, Hava recently was awarded the Meritorious Public Service Medal from DARPA. And this is the third highest honor that the Department of the Army can bestow on a private citizen. So it's great to have Hava back, and we are delighted with this award. Today, she's going to discuss how insights from natural reasoning systems can inform the design of artificial reasoning systems. So with that, over to you, Hava.
Hi, my name is Hava Siegelmann. I direct the BINDS lab, and I would like to present a bit what we're doing. So in general, what we do in the BINDS lab is we looking at AI and we're looking at neuroscience. We try to find the relationship between them. Indeed, AI started with looking at neuroscience, and we repeat this process. Today, there are many groups that are looking either at one of them. We find that by looking at both, we can still ask bravely, what are current limitations of AI? Can we go back to neuroscience, find ideas? By doing that, I would like to show you some examples. So the first limitation of AI today, I think, is that AI is frozen after it's programmed or trained. So if you talk about AIs from the 80s, like rule-based systems, it's all written if then else, and everything had to be processed in advance. The other option that is working today is neural networks that are shown examples, but the examples that are shown are through a training set that gives all the possible input outputs that somebody prepared in advance. So what happened is that the neural network load this data, and that's it. From then on, it's frozen just like the previous AI. So in reality, once we prepare AI, either way, AI or machine learning, it's frozen after preparation. And the similarity will be, if you want to think about animals that got through genetics information, and after that are not able to learn. So as they go, as they have things that they are doing, they cannot learn from their experience. That's kind of where I today. And the issue is that without this capability of lifelong learning like animals, there are malfunctions and there is a lack of reliability, because if you are in new circumstances that were not thought before, then it's not working. So if you want to look at this little figure, time is on the x-axis and performance on the y. So during training, performance goes up. and then it stays still. In fact, if you had a system that could learn from the experience, like a car, then the car will drive better and better, let's say on snow. But if you cannot open to experience, it can never get better. And in reality, if you get to things that it doesn't know what to do, it fails. What we want to have is that type of AI that continue learning with this experience, so it becomes better than in the end of the training set. And also, when it sees that things are not there, it opens itself. So that's kind of lifelong learning. And I was recently in DARPA, and I founded and managed this lifelong learning machine. And the idea was that I describe or define different pillars that will bring to lifelong learning. And many groups join us. It actually was a very large program, and worked together on these different pillars to create this vision of lifelong learning. What I will show here from the lab is just talking about class incremental continuous learning and generalization, just two of the pillars. And the importance in lifelong learning is that we see new behavior at the end. So it's not just the system learned, but it actually uses it in order to provide new behavior. So let me start with the first one. The first one is the continual learning and class incremental learning. So if you look at the left here and the bottom left, we see that there are many methods that were suggested for what is called continual learning or task continual learning. So for example, if you have many letters, one task will be to separate between 0 and 1. Another task will be to separate between 4 and 5. And all these methods can do that. They learn every time one task. And when you come to it with a question, you have to tell it which task it is so that they know to separate. So in fact, they're so good in separating 4 and 5 and 0 from 1 that it can never separate 1 from 4 or 0 to 5, because this is outside of what it learned. It's not a task. So this is not a very nice thing. If it was a person, you'll say that the person is an idiot. In lifelong learning, if you learn to separate 0, 1, and then 4 and 5, we want it to be able to separate all the other options, because that's what you do when you learn from your experience. So recently we suggested one way to try to do that. And this is by brain-inspired replay. It's a joint work together with Guido and Andreas from Baylor School of Medicine. So in general, if we learn something and we're now ready to learn another task, and we don't want to forget the previous task, one way to do is to keep everything that we learned in the past, and every time that we want to learn a new thing, so that the new thing will not create catastrophically forgetting for the old, will bring also the old and retrain it. So this idea of retraining was there in AI, but it's a very expensive and unscalable idea. It's also very not biological. You cannot just say, oh, I forgot what I saw in Italy last year. Let me be there again so that I can see it. So we don't have that capability. So what we have capability is we cannot do retrain, but we can do replay, which means that we cannot really take the set as it was there, but we can generate. So if we generate things and bring them back, maybe that will allow us to learn a new task and remember the old task. But this is also not working very well. There are many papers tried to do that, not that successfully. So what we decided to do is to go to more details and to have brain-like generation. So the idea is that once we generate, just like in the hippocampus, we'll not generate all the way to the output. We'll just generate to some level of abstraction. And you can think about it as what happens in dream. You don't generate what you saw exactly perfectly. You don't have in your dream perfect input, but you have something that is like. So this is some level of abstraction. And interestingly, once we do that, first, it's very fast. We don't have to have very good like input data, but once we do that, learn just a little bit and then retrain, we actually get what we wanted, which is not just the task incremental learning, but the clustering and the classes incremental learning. So as we see here, we go through abstraction, and that kind of brings us to another idea, which is how we can do abstraction. You know, in general, abstraction is very important in AI and also to human, because if I saw a few examples and I can abstract them, I don't need to see these examples again. I already understood the idea. I can apply it to another things. I can do analogs and really kind of smart way of learning is because of abstraction. So the question that we came, this is only at the Bynes Lab, Patrick postdoc, Nick and Javier were two grad students. So the question is, how does the brain, the human brain, do abstraction? So what we notice is that if you look at the connectome, which is the way that the brain is connected through pathway and through measurements of MRI, if we look at the connectome, there is something very interesting. Actually, the connectome enables this abstraction. And I'll tell you very shortly how. So let's say that you look at the visual cortex, which is here, and you activate it. And after a short time, you see where the activation is in the brain, where it propagated next, where it propagated next, where it propagated next. And you can look like that until it kind of going around in the brain. And the one that is outside, let's call it visual being 1. And then we go to visual being 2 and 3 and 4. And let's say that we take the whole continuum and we cut it to 10 times so that we'll have 10 beams, which tell us how far we are from the visual cortex. The same we can do for the somatosensory cortex, to the olfactory, to the smelling. So we can do olfactory, we can go like that, and we can summarize and average them all. And in that we take the whole brain and we put it in bins, which bin number 1 is the closest to the outside, and bin number 10 will be the deeper that we can. And the question comes, if we have particular tasks to do, which is related to abstraction and to different way of thinking, where will this fall? Will they all fall if they're very basic and they're just about like finger tapping, will they all fall in bin 1? Or if it's very abstract, like thinking about democracy and love and fairness, will that fall in bin 10, in the deepers? And the question is, how can we look where it falls? And for that, we take functional MRI. In functional MRI, we see the hemodynamic. We see where the blood is moving around in the brain. And we can correlate where the blood is moving to activity of neuron, because blood brings sugar and oxygen, which is what is used for neurons to fire. So when there is brain activity, they immediately calls on for more blood. So we can look at fMRI. We look at 25 years of information of people that were asked to do a lot of activities in many countries, lots of experiences, and we look where they fall. And we realize first that when we do different tasks, they never fall in one bin. They actually fall in all the different bins. But what is interesting, they fall in all the different bins in different ratios. So what we did is we look for every experiment. Let's say the experiment was to memorize something. And we look, let's say, at 1,000 cases, 1,000 times that people did experiments like that. We took all the activity and we treat it like data science. So now we said, okay, let's look where the activities are more or less, and we draw a line, we look at the slope, and if the slope is negative, it means that most activity was outside in early bins, and if the slope is positive, it means that most activities were done deep inside. And we take all the activities that we see all the behaviors that we see, and we put them by slope, starting with tapping and going all the way up to naming. And you can kind of already see that these kind of behaviors become harder, more and more aggregated. Then we did another task to ask people to explain to us what is more abstract with what. And voila, what we realize is that the brain connectome is actually allowing us to have this kind of hierarchy, which is related to abstraction. So when we want to do high abstraction, it's very deep in. So this is an interesting idea by itself, but recently, just last year, student Alex Game from Bynes managed to demonstrate that we can actually use it for very important problem of neural networks. So this important problem is we can take a neural network and train it on some training set, but how do we know if this is a good neural network to generalize beyond the training set, to test set, to other things that we'll see? So given, let's say, 10 different networks, which is good one for this task, which will be good to generalize? So what he noticed is that the same thing that happened in the brain happened also in deep networks. So if you look at more complex input, maybe like this 8, then the activity in a well-trained network is in the deeper layers. And if we start with more simple input, then the activities are early on. And we can see the slope for 1 is very negative, the slope for 8 is very positive. And the reality is that networks that have this high correlation between the complexity of the abstractness of the input and between the higher slope will be the ones that generalize very well. We compare to all other methods that try to find how well we generalize on numerous data sets and numerous options, and we find very clearly that our methods that we called CNA for cognitive neural activation metrics is interestingly finding the best prediction for every neural network, how well it will do on generalization, which is a very good and applied problem that was very needed. There is another key limitation, and this is about robustness. So if you see this student is from Georgia Tech, he's a friend of us, and all his life he wanted to look like Brad Pitt. So we gave him these glasses and voila, the systems say Brad Pitt. And then, you know, you go around in your car, speed limit is 15, and you really don't want to drive so slowly. But if we just add this little part here, the speed limit is 65, you can drive faster. And what about stop sign? You see, the system doesn't really recognize this stop sign there. It says that there are people there, other people there. Actually, it seems that the network was right. So there are differences between networks and between humans. We see things differently. And in reality, it's this extra sensitivity to patterns that make AI stronger and make AI not robust. So in DARPA, I also introduced another program, which was called GUARD, for guaranteeing AI robustness against deception. And after that one, I introduced 2 other, which is RAID for re-engineering of deception and reverse engineering of deception and secured training. But what is important here that there's no one answer. There is not one answer for whether something is strong or weak. The one answer is it is strong under some situation. And that's why we build there a test bed, which will say that my thing is robust if it's 10 hours outside and you have this and these computers. And under this, we can say things. I want to give you just a little bit of the taste. The first taste is that people who suggested explainable AI is a way to make AI safer actually realize that it's very wrong. It's very easy to give you what you told us, how to explain things to you. It's very easy to trick the explanation. So if I have to separate between safe time and non-safe time, and I tell you now it's non-safe time because 1, 2, 3, 4, but this 1, 2, 3, 4 are not there. Another thing is that we cannot only rely on computed confidence because it's very easy also to trick confidence. So it takes much more to get into robust AI, which is one of the things that we also work in the Binds Lab. In general, if you think that one person wants to have, you know, a prosthesis, you want this prosthesis to be trained in the factory, but not fully trained because you want it to be trained to yourself. You want it to generalize because you walked in one room. Now you're in another room. It's not exactly the same, but it's similar. You want it to be robust that other people cannot trick and get into that and cause you to jump from the window. So in general, there is a hypothesis that perhaps in a few years, what we consider non-neural networks, which is this pattern classifier, perhaps will not be considered really AI, if you don't have lifelong learning and generalization and robustness. So these are something that the Binds Lab is working on. In addition, we ask for what other important things that we have to put to AI. You know, humans, our character is so much our memory. So whatever we remember, who we are, what things happen to us, is doing the kind of giving us who we are. And can't we give memory like this to AI? That AI will know who they are, will start having their own ethics, their own favorite things. Another issue is the partnership between computers and humans. It's beyond explanation and beyond ease of communication and beyond trust. How would you like to communicate with your friend? Why wouldn't you communicate like that with your AI? Then we care a lot about computational capabilities of natural systems and how we can take ideas from it for AI that will have better capabilities than today. And we also have been working for the last 5 years on ethics and morality. So if you want to hear more about Binds, please come over and we'll tell you everything. Thank you very much. Bye-bye.
So thanks, Hava, for that and for joining us here on stage. Welcome. You are muted, so you'll want to unmute. So we do have a question that notes the relationship, that at least at first approximation, the relationship between your neurologically inspired work and what Erik Learned-Miller spoke about earlier about learning from experience. And so the question is really, does the angle that you are taking in the Binds lab lead to like very different neural network architectures, or are you using existing architectures but running algorithms over them very differently? Because it looked, at least at first approximation, that the Erik's learning from experience was kind of building on existing neural architectures and existing neural algorithms, but training them in novel ways. So could you maybe explore that little
Definitely. Sure, definitely. I think that I mentioned in the talk that I was in DARPA recently and started a program called Lifelong Learning Machines, where we want to do these things. So from all UMass, we had only one person who was supported by us, and this is Erik Learned-Miller. We actually supported him to do lifelong learning. So he's one of the many people in the world and many people in the United States that are part of this program. So the similarity is not to be surprised, because that's kind of the effort that he's talking about. Regarding the detail, there are various ways to do that. I think we have the view, perhaps because a particular view of various options that there are in order to make the network better, to enable new type of neural networks and structure beyond what exists. So in the work that we currently do, we combine different approaches. Some is to build on existing architecture but change them, and others actually to introduce different ideas. So I can tell you a little bit about the other ideas. So we know very well that the brain is not made of the same kind of neurons. Mm-hmm. We need to have inhibitory and excitatory. There are various kinds of inhibitory. Two of them are particularly important, short-term, and that make sure that neurons that fired a lot recently can rest and until they get energy, and others that have a little long-term effect. And so in the lab, we're looking, for example, as part of the things on these various type of neurons in the same network, which provide kind of a different view. And yeah, also we're looking at so when you talk about neural networks, we usually have this big simplification that the way that they're related between themselves is the weights that are connecting. And the classical thing is that all the neurons update together. The reason that people take that is because it's very easy. Then you multiply all the neuron value with the weight value and get the next one. But it's very not biological, and also it has issues. So we're looking also at asynchronous network, where things are kind of update when they are ready. and we're not forced them to update together. We get, because of that, we get time-aware machine intelligence that can get the idea if something is just before the other, something just after, we kind of start getting kind of causality and effect of the, so, and various others. So just to say, yes, both of them.
Excellent, excellent. Well, I know that this is, we can talk for hours on this one. So, but I'm going to just thank you so much. We're going to move on to our next speaker, and Hava, again, invite you to join us at right after the session for anyone who wants to pursue this a little bit further. So thank you so much, Hava. So we're going to now move on to our next speaker. Our next speaker is Marco Serafini. Marco is a member of the Dream Lab along with Jerome from earlier today, and he's also leader of the Data Systems Group. Today, Marco is going to discuss his research on machine learning over data organized as graphs. Over to you, Marco.
Hello, my name is Marco Serafini, and I'm an assistant professor at CICS. I lead the Data Systems Group. Let me tell you more about the research of my group. So the research areas of my group are at the intersection of systems and data. So we look at issues such as performance and scale, usability and programming abstractions in the context of graph data management, graph data analytics, and machine learning, and combinations of these two areas. Let me tell you, for example, about one area I work with my students, which is machine learning on graphs. But before I go there, why focus on graphs? Well, graphs are a universal formalism to represent all situations where, all data sets where we want to extract information, not just from single entities, but also from their relationships. And there are many use cases where you want to do that, from relational data to security to recommendations and social networks, NLP. So what you do in this case is you extract a graph from your data, the graph structure. And sometimes when you do that, you integrate multiple data sources, and then you obtain a graph which you can use for further analysis. It's a very flexible formalism. Machine learning on graphs in particular is becoming increasingly popular in many applications, such as search, Q&A, semantic web, where you have a knowledge base and you want to integrate deduction from this knowledge base with induction from text, information that you extract from the text, and also personalization and recommendations. So for example, if you have, you could have a graph that represents users, their relationships, whether they buy or they like certain products and how products are connected with each other. And then you can use this information to recommend products to users. So one important intermediate step when you perform machine learning is representation learning. So instead of coming up with features yourself, it's often better to use a neural network to find the features of the relevant features of data, which may be hidden. For example, in natural language processing, it's very common to extract embeddings for words. So each word is assigned an n-dimensional vector, which is called embedding, and this n-dimensional vector encodes the hidden features, which sometimes can have a semantic meaning, right? So we can use vector algebra to find interesting relationships between the meanings of the words. And once we find, so in order to find these word embeddings, we train a deep neural network. Once we have these embeddings, we can use them in downstream tasks like named entity recognition. Now you can do something similar for graphs, where now you typically learn features for vertices. The difference here is that instead of learning these features from, like in the case of text, you learn features from other words that are close by to the word you're learning the embedding for in sentences. in graph neural networks or in graph representation learning, you want to learn the properties of one vertex from its neighborhood. So it could be one hop, two hop neighborhood from random walks, and in general from the graph. And then again, once you have these embeddings, you can use them for some downstream task. Now, in the context of graph machine learning, actually, graph neural networks are an interesting emerging architecture of neural networks, which you can see as an evolution, yet another class, important class of neural network architectures, which is tailored for graphs, just like convolutional neural networks, for example, are tailored for images, or recurrent neural networks are tailored for text, natural language, and sequential data. The big difference here, though, is that unlike for RNNs and CNNs, with graphs, data correlation does not imply data locality. So in graph neural networks, the idea is that we obtain the features of a vertex by aggregating the features of the k-hop neighbors of the vertex. And at every step of aggregation, each vertex aggregates from its neighbors using neural network layer. Now, the problem here is that this neighbor-based aggregation performs a lot of random accesses, right? Because I need to get neighbors from different memory locations, and this becomes an important bottleneck. So this aggregation is an important performance bottleneck that does not arise in other architectures. Another problem that arises on graphs is how to use mini-batching. So in mini-batches are a sample of a subset of the input data that we use for one training iteration. And typically, when you have data sets that are discrete, you can simply pick different points in your data set independently and form mini batches that way. But in graphs, it's different, because as an input, you get one single graph, and now you need to extract mini batches from it. And the way you do that is by sampling the graph, for example, sampling the k-hop neighborhood of a subset of the vertices. And there is a growing literature on how to perform this sampling. So there are different algorithms with different properties. The challenge here is that actually graph sampling algorithms do not leverage the GPU. So the typical approach is to run sampling on the CPU. Then, because of this random access, like before, by doing graph sampling requires a lot of random accesses. So people do typically random sampling on the CPU, and then once they obtain the mini batches that way, they can actually run the training on the GPU. The problem is that doing that makes sampling become an important bottleneck. So we have measured that it could take up to 62% of the total training time if we use one GPU, and if we have a node with multiple GPUs, the one CPU is going to become even more of a bottleneck. So my research group actually is looking into several issues related to get systems for graph neural network training. So we have just completed work on a project called Nextdoor, which significantly speeds up sampling using GPUs. And the idea is to both provide programming abstraction, so an API to hide the complexity of GPU programming, while at the same time offering the machine learning experts the possibility of implementing their own sampling algorithm, and while at the same time providing much better performance than any CPU or GPU-based implementation that exists. And that's thanks to a new approach to parallelism that is specific to sampling. And for example, in the slide, you can see how easy it is, for example, to implement two-hop sampling using Nextdoor, just a few lines of code, and you get a very efficient implementation. Ongoing work from my group is on speeding up distributed sampling and training. So very often, actually, graph neural networks are run on large graphs that don't fit in memory of a single machine or a single GPU, even less so. So how to actually distribute the sampling and the training, in particular, since now with Nextdoor, we have enabled running sampling efficiently on the GPU, how do we actually schedule the GPU resources, and how do we coordinate this process when we get even less data locality because we might have to fetch data from different sources. And also we are working on speeding up graph neural network trainings on GPUs, not just the sampling process, but also the training. And the idea here is to increase GPU utilization by using techniques like operator fusion and resource scheduling. Now, another big area from my group is querying and storing graphs. So in previous work, I have worked on graph mining applications like frequency graph mining and motif counting. And I have developed Arabesque, which was the first general system for graph mining. Basically, you can think of it as a MapReduce for graph mining. You could run graph mining with a simple API or a distributed system and very efficiently. So today there have been several follow-up works on graph mining that have built on the experience of Arabesque. So what is the next step, the next problems? So a recent survey from users of graph tools have highlighted some important pressing needs and ways ahead for this type of system. So first of all, it has shown that many users have to deal with large graphs, that these graphs are dynamic, so they change over time, that they are stored on a distributed system. And actually, there are many applications that are latency sensitive. So we want to run graph analysis fast. The faster we run it, the better. And as central concerns for these users, people have mentioned scalability and performance. So for example, examples of applications with these characteristics are, for example, recommendations and question answering. So companies like Alibaba and Amazon and Pinterest, they use actually graphs for recommendation and question answering. And in some cases, actually, they need to query the graph with very low latency. A similar example is when we run fraud detection and companies that financial institutions that run fraud detection or even online stores, and they have a graph of financial transactions and they need to detect patterns in this graph that denote potential frauds. So in my lab actually is working at different layers of this stack. So in previous work I have worked on transactional storage. So how to build a storage system that is able to accept dynamic updates while providing similar performance as read-only, read-optimized storage. Current work is actually on running distributed graph queries with strict latency bounds. So you can reduce the latency of a query, especially in graph queries where queries need to hop potentially from one server to another and perform multiple hops. You can use replication to minimize these hops. However, you want to replicate as little as possible in order to achieve your goals, your latency goals. So one of my research projects of my students is how to coming up with algorithms to replicate data in an efficient manner. And finally, another project is actually online indexing for graph queries. So because graph queries are so computationally intensive, people have looked into using hardware level features like CPU vectorization to speed up the process. And typically one way to do that is to index the input graph in a format that is friendly to vectorization. However, this is very expensive. So we are in one project, one paper that is currently under submission. We are looking into how to actually speed up this process by doing indexing online, not as a preprocessing step, but during query execution. And that's actually much more easy to run when you have dynamic data, and preprocessing might be unfeasible. So finally, one last area that I'm working on is data management for machine learning. And as we have discussed, a common machine learning pipeline is to first learn the representation of your data, come up with some embeddings, and then run some downstream task. Now, the one important issue in terms of systems for machine learning is how to store these embeddings and retrieve them efficiently. So some of my students are looking into how to index embeddings, how to store them efficiently, how to integrate an embedding storage system with existing machine learning pipelines, how to enable transactional updates, multi-versioning while providing efficient access. And in particular, right now, the focus is on running nearest neighbors efficiently on large data sets of embeddings. That's it. I would like to thank my wonderful students for all this research that I have briefly discussed and the sponsors of my research. Thank you very much.
They're reminding me to unmute. Thank you, Marco. We are running a bit behind schedule. We have a very tight schedule today. And so I'm going to just, because we're going to be having a separate session at the end for Q&A, I'm going to, with just regrets and apologies, just move on to our next speaker. So please forgive me, Marco, but join us in the Q&A session afterwards. And I want to just then introduce our next speaker, Hamed Zamani. Hamed is the Associate Director of the Center for Intelligent Information Retrieval and an assistant professor here in CICS. So today, Hamed's going to discuss his research on interactive information access systems. So over to you, Hamed.
Hi, I'm Hamed Zamani, and I'd like to talk to you about our research on proactive conversational search and recommendation. Just a little bit of information about me. I'm an assistant professor at UMass Amherst in the College of Information and Computer Sciences. I also serve as the associate director of the Center for Intelligent Information Retrieval. My research interests are developing and evaluating statistical and machine learning models with application to information access systems, such as search engines, recommender systems, and question answering. And my current projects involve developing neural models for information retrieval tasks, weak supervision for information retrieval, and also conversational information access, which is related to this presentation. Just let's look at an example of how users interact with a search engine, which is basically one of the most important and most successful applications of information retrieval and computer science in general. Assume that I'm looking for information about coronavirus while traveling. So I search for coronavirus and go through the result list, look at the documents. I may click in some of the documents. And if I don't find the information I'm looking for, I reformulate my query. I search for coronavirus travelers. And then I go through the result list. If I don't find the information I'm looking for, again, I reformulate my query. And then here we are. The first link is the actual relevant documents, the ones that I'm looking for. So with this example, I'm just showing that how limited are the interactions that we can take with search engines. The users can just submit a query. The system responds with the result list, with the search engine result page, and the user can just click on one of them or just submit another query. But think of these devices with limited bandwidth interfaces, such as small screens, or in this extreme case, a system with no screen and voice-only interface. So the users cannot go through the result list using this interface quite easily. We believe that we need to go beyond this query response paradigm that we currently have in the search engines. The systems can be able to take different actions other than just responding to query and providing a result list. But one may ask why this is the right time to focus on conversational information seeking, and why this is the important problem. The first reason is the recent advances that we observe in automatic speech recognition. We can get reliable transcriptions of speech utterances in several languages for many different accents. So these are just some becoming a reliable way of interacting with the systems. Devices with limited bandwidth interfaces are becoming more and more popular, and users are spending more and more time interacting with these devices. The third reason is the recent advances in deep learning that makes natural language processing and generation more powerful, and we can kind of imagine how we can generate responses to a lot of queries instead of just retrieving them. And the last one is the importance of information access in all of these systems. Everywhere that we have an intelligent system with a lot of information, we need to provide a gateway to those information. We need to provide a way that the users can access those informations. And search is definitely one of the ways to provide these access. So there are a lot of challenges, major challenges in developing conversational search and recommendations. The first one is these limited bandwidth interfaces. Most importantly, when we want to present the result list, we need to develop models for multi-document summarization, or more importantly, explaining the result list to the user. These systems often consist of multi-turn interactions. So the system needs to be stateful and interactive. They should be able to keep track of all of the previous interactions that the user had with the system. The third challenge is about multimodal interactions. These devices that we deal with usually have different modalities for interactions, for example, speech, screen, and we can imagine different ways of interacting using virtual reality and augmented reality devices in the near future when people want to just make conversational interactions with these devices. The last one is the need to go beyond this query response paradigm to make mixed initiative interactions in conversational search. This is the actual focus of this talk. Let me give you an example. When a user searches for a query like COVID-19, instead of showing the result list related to this query, the system can decide that, okay, this is an ambiguous query. This can be related to, for example, general information about COVID-19, or it can be about new cases, some new statistics of COVID-19. So the system can decide, instead of showing the result list, let's ask a clarifying question to make sure what the user actually needs. For example, say, what do you want to know about this medical condition? The system can also show some predefined answers, some candidate answers to its clarifying questions, such as symptoms, precautions, recent news. Clarification is one type of mixed initiative interactions that we are looking into. And we developed a general framework for generating these clarifying questions in open domain setting, and for example, web search setting. In this framework, for each query, we have a query aspect generation component, which kind of generate all of the aspects of the query. These aspects can be generated from a knowledge base, in the simplest case, or it can be mined from search logs or the search engine result page. Once the aspects of the query are generated, then we generate the question using an encoder-decoder neural network. This basically encodes all of the aspects that we generated in addition to the query and then the coder generates a natural language question. The third component generates a set of candidate answers for this question. The candidate answers can be selected from the query aspects, or they can be generated from the question itself. And at the end, there is a clarification utility function, which kind of is used for optimization of our model. This component maximizes the probability of clarifying the user intent by asking the question. So basically, it's maximizing the probability of C equal to 1 given the query, clarifying question, and candidate answers. C here is a binary random variable where C equal to 1 means the different user intents are clarified using these clarifying questions. We have developed 2 public benchmarks for these tasks. One of them is a small scale with 200 queries, but the questions and candidate answers responses from the users are all human generated. We collected them through crowdsourcing. The other data set contains over 450,000 unique queries. These are all real queries submitted to the Bing search engine. This was created with our collaboration with Microsoft. And the questions in these data sets are machine learning generated using a model similar to the one I just presented. And this contains a lot of real user interaction signals, such as click on each individual options. Let's go beyond clarification. For designing proactive conversational systems, the systems should be able to initiate a conversation. For example, once there is a conversational system sitting there, and once they decide to initiate a conversation, talk about something, we compiled a taxonomy of agent-initiated interactions. It has 3 dimensions. The first one is initiation moment, basically answering the question of when to initiate a conversation. It can be instant initiation for scenarios where it's, for example, related to health or safety that we need to instantly initiate a conversation. Or it can be an opportune moment initiation. We need to wait for a suitable time and then initiate the conversation. The second dimension is about initiation purpose. Why to initiate a conversation? There can be different reasons. For example, filtering some streaming information or following up a past conversation. For example, you had a conversation with the system in the past and the system provided a wrong answer. And later on, based on new information, based on new deployment of new models, they understand that, oh, we provided a wrong answer. They can follow up. Oh, do you remember that we talked about this question and I gave you this answer? Okay, I was wrong and I realized that this is the new answer. This is the correct answer. They can also contribute to multi-party human conversations. For example, 2 people are talking and one of them says that, okay, only a couple hundred of people have died of COVID. So the system can run a fact checking and initiate a conversation due to some credible sources. Unfortunately, we have lost over 500,000 people in the United States due to the COVID. So these are different purposes of initiating a conversation. And the last dimension is about initiation means, or how to initiate a conversation. For example, if the user has multiple devices, or if the device has multiple modalities, which interaction modality should be used to initiate a conversation. We developed a high-level framework for initiating conversations. Basically consists of the first component is related to initiation purposes. So it gets all of the information such as past user system interactions, user profile, streaming information, and then identifies what are the information that we want to produce, what are the initiations that we want to make. And then there's an initiator component, which is about initiation moment. So it decides when to initiate a conversation. And once it decides that this is the right time to initiate a conversation, the third component generate the conversation and select the modality and the device and kind of interact with the user with the initiated conversation. To make all of this research possible in the research environment, and also with practitioners when they want to kind of build new systems, new models, try out new scenarios, we developed an open source platform for research and conversational search and recommendation. It's called McCallum. It's available in the link in this slide. And the McCallum is basically using a modular architecture. It consists of processing the interaction that the user had with the system, logging all of these interactions, and then dispatching these interactions towards multiple information access systems: search, recommendation, question answering, generating clarifying question, and so on. And then at the end, it decides, okay, what response should be chosen, what modality, and then represent the results to the user. This is an example of an interface that we had in Miklau. It's basically supports multimodal interactions. The user can talk to the system. It has automatic speech recognition. It provides different types of responses, such as text or a list of clickable options or links or images, and so on. And these are just some examples of the work that we do related to proactive conversational systems. There are many more. For example, joint modeling of search and recommendation, developing new models that jointly represent items for search and recommendation. Multimodal conversational search and recommendation, supporting multimodal interactions and also multimodal information items. Modeling and measuring conversational search and recommendation, especially through an economic model of conversation by estimating the cost and benefit of each interactions and estimating what would be the optimal interaction that we can take at every moment, and many more. At the end, I'd like to thank all the collaborators I had throughout these years. And in this, I'd like to talk a lot about the research that we do at the Center for Intelligent Information Retrieval. It's not just about conversational search. We do a lot of fundamental research about deep learning for search engines and recommender systems. We work on misinformation and controversy, and also explainability and fairness. So feel free to reach out if you are interested in any of these problems. Come talk to us. There's the link to our websites. Go and check out our kind of current and ongoing projects. Look forward to hearing from you.
Okay, thank you, Hamed. So as with Marco, we're a little pressed for time. So we're going to move directly on to our last speaker of the day. I'm going to remind everyone that we will have a Q&A session in a separate Zoom meeting immediately after our final speaker for anyone who would like to follow up with any of today's speakers. So with that, let me take a moment to introduce our final speaker of the afternoon, Andrew McCallum. Andrew is a distinguished university professor, and he's the director of the Center for Data Science. He, as is common with this rarefied group of distinguished university professors, Andrew has a long and very impressive bio, which I don't have time to share with you today. I am simply going to say that Andrew needs no other introduction, and I'm going to let him share with you some of his recent research in information extraction and synthesis. So over to you, Andrew.
All right, thank you, Brant. I'm very happy to be with you all today live. My collaborators and my research focuses on machine learning and natural language processing applied to document collections. We'd especially like to help enable good decision-making for people like this, who are faced with information overload. And one particular category of people who are faced with overload are scientists who are faced with a rapidly increasing rate of publication. In fact, in biomedicine alone, there are over 4,000 new papers published every day. In a recent survey of scientists, 85% of them said they believe they're missing important new research in a typical month. And 73% said they wish they could be more up to date. And the difference, who I guess don't wish they could be more up to date, have basically just given up. We have been working for quite some time on building tools that help scientists do their job well. This includes work about a decade before Google Scholar existed on a system that has very similar functionality. When I arrived at UMass, we built another more up-to-date system that knows not only about people and papers, but also about institutions and conferences, journal, grants, advisors, etc. You can consider all of this to be the metadata of research. And now we're especially focused on the underlying core data about the process of science in an effort to build a map of science, a knowledge base of scientific entities and relations between things like materials and equipment, organisms, diseases, processes, tasks, and methods, for the sake of building tools that will help accelerate the progress of science. And in this project, we have been just so fortunate and so thrilled to have as a close collaborator the Meta project at the Chan Zuckerberg Initiative, who have been building a very large knowledge base consisting of both metadata and core scientific data. And it's been just a very satisfying and beautiful collaboration over the course of 5 years. Here's another example of a different collaboration with an academic partner. With Professor Elsa Olivetti at MIT, we have been building systems that consume hundreds of thousands of research paper raw text, extract from material science, extract from them essentially the structured recipe for how to cook up a new batch of, say, car battery material of the future, and then mine the resulting database for patterns so that the machine can automatically suggest new recipes that have never been tried before that may yield good results. We've also been collaborating with government, where we're very proud to have our technology deployed at the US Patent and Trademark Office after having won an international competition for inventor disambiguation. So now I want to spend some time talking about the process of how to go from raw text to knowledge representation to reasoning. And let's start by focusing on knowledge representation from raw documents. How should we represent knowledge? One way to do this is just to keep around the raw documents themselves, the raw text itself, kind of like a basic search engine would. And this has great fidelity to the original evidence. However, it can be difficult to reason about linked data, or what I mean by this, to reason about entities that with information that may be spread across many pages, and we would have liked to integrate that data in order to reason about them more robustly with information that combined from multiple different sources. Based on that motivation, many entities, including big ones like Google, have worked on building knowledge graphs that assemble in one node of the graph a lot of the information from many different sources about one entity and also capture relations between them with edges. These are typically mostly human engineered graphs in which both the data and the schema of entity types and relation types was designed by humans. These are great and address the concerns that we had previously, but they bring up new concerns about generalization and coverage. The human designers just often don't think of every last detail that might be useful downstream. A third option are parametric models. For example, deep neural networks, which especially recently, with models that contain literally many billions of parameters, can indeed store vast amounts of knowledge and have been shown to have great generalization ability. However, they give rise to new concerns about whether the degree to which the models are reliable. To what extent may they be hallucinating information that may not be true, or are they inspectable? Can we know what do the models know and what do they not know, or are they manipulatable? Can the maintainers of these models reliably add new information or subtract information from these models? So in response to all these concerns, we've been working on a method of knowledge representation that aims to combine the advantages of all three of these, in which we keep around the raw text, we run some local neural networks to do interpretation of the raw information in each document. We also integrate information that may come from pre-existing structured knowledge graphs about entities at the top of the slide. And then mostly the research consists of how to link these together in such a way that dynamically, as new documents and new evidence arrives, we can modify the graph above and also keep track of exactly where to find the evidence for each one of the new pieces of knowledge that we insert into the graph above. So there are some parameters in the graph above that capture some generalities about the graph, but really most of the learning and the parameters sit in these linkage functions that explain how evidence is tied to knowledge. This is a bit abstract, so let me give you an example of what I'm talking about. Here's an entry from Google's knowledge graph for this particular person. Again, this information was mostly gathered by hand, and also the schema was built by hand. What do I mean by schema? It's like the entity types, like the fact that she is a Norwegian psychologist, and the relation types, like her spouse, her education, and awards. The schema of relation types spans quite a bit of information, but it doesn't cover everything for which there's raw information in the text. For example, it says nothing about who she was criticized by, even though that appears in numerous documents and could be interesting to downstream researchers. So what we would like to have is a knowledge base with an open schema that can capture everything that would have been said in raw text, like a search engine would be able to, but at the same time have a very distinct entity relation structure in a graph, and that also supports reasoning. So how do we do this? Let's take a more general knowledge graph here and consider some text that may support this. We start with the text. We find mentions of entities in that text using natural language processing. We do entity linking so we can find all the mentions of the same entity, even when they may be spelled different ways. We gather the list of all the different entities and all the different entity pairs that appear near each other that may support relations. And then we can, say, gather some pre-existing database with existing schemas that capture some information we already know about these entities and relations. And we also might like to import additional databases that also know about these entities and relations, but those databases that were made by somebody else invariably will come with some different schema that's not exactly the schema of our original database. We'll preserve the fidelity of that different schema by just keeping that schema as well. And then, somewhat magically, we'll also use the textual expressions around these entities to form other schema items. And this leads to a massive and indeed, yes, highly redundant schema, but that nonetheless preserves the fidelity and all the subtleties of what might be said in multiple structured knowledge bases and in text. So, for example, if we ask the system, was Obama president of the United States, we can see that that was directly observed. And so we can say yes. If somebody asked, well, was he the leader of the United States? Well, that was not directly observed. It's just, there's just a blank in this graph, in this matrix capturing the knowledge. But we would like to be able to answer such a question by generalizing from what we observed. Filling in this matrix with generalizations is a matrix completion problem, which is exactly analogous to what Netflix does when it predicts which movies you will like when you only rated a few of them. And the classic way to solve this problem is by doing matrix factorization, which essentially learns a vector in some relatively low dimensional latent space for each row and each column of this matrix. So say there may be a 200-dimensional vector associated with each entity pair and with each relation type, and we use the dot product between these vectors to make predictions in the matrix. So in the end, this results in a knowledge graph that on top of each of the nodes and the edges of the graph has not just symbols, but also vectors that capture the semantics of the graph that allow for more generalization and allow us to express knowledge that came originally from text. All right, lastly, to wrap up, I'd like to describe in further technical depth a new twist on this about which I'm quite excited. And that is a replacement for these vectors that also generalizes, but has some new capabilities. And let me introduce it in the following way. This is joint work with my students, Lorraine Lee, Dongzhu Zhang, and Luke Vilnius, and my postdoc, Michael Baracco. So vectors are used fairly universally in machine learning to represent concepts, and indeed they can be very useful. We can, for example, capture the notion that various different kinds of furniture are semantically near each other, as are various different kinds of animals. But they do have some disadvantages. For example, nothing here in the vector captures the notion that a mammal is a much more broad concept than a rabbit. And so they don't capture broad concepts and narrow concepts. There's also no asymmetry in a dot product between these. Though a rabbit is a mammal, but a mammal is not always a rabbit. In response to this, a few years ago, we did research in a Gaussian representation per concept, essentially like an oval-shaped bump in space, which indeed can which we can use to represent broad and narrow regions with wide ovals and smaller ovals, and can also capture containment. So we can capture this notion that, say, a rabbit is always a mammal because it's contained inside the mammal oval. You can think about these sort of like learned Venn diagrams. Gaussians are nice, but they are not closed under intersection. The intersection between Gaussians is not always a Gaussian, and that's a little bit sad mathematically for various kinds of downstream reasoning we'd like to do. Another approach that can be taken is one called cone representations, in which each concept is parameterized by a vector, but our interpretation is this vector implies a region that spreads away from the intersection in all dimensions. So here we can see that a rabbit is an herbivore, or because it's contained inside the cone of herbivore that spreads away from the origin in the lower left. We can, these models are closed under intersection because, say, the intersection between mammals and herbivores is represented exactly by this brown dot that just appeared. However, there are some problems here. Every concept will eventually overlap with all other concepts. So there is some region in the far upper right here that represents being both a rabbit and a deer at the same time, which should not be possible. And furthermore, if we ask, well, what's the probability of being a rabbit condition, like given that you're already a deer, what's the probability of also being a rabbit? Well, this focuses on this part of the space, and actually the probability is very high, which just seems completely wrong. In response to this, we have been working on these models that we call box embeddings. They represent each concept with an n-dimensional rectangle in space, say a 200-dimensional rectangle. Here, we can also represent containment, asymmetry, concepts can be disjoint, and boxes are also closed under intersection. So here we can see, say, like the box that would capture those things that are both herbivores and mammals, and that is also a box. Furthermore, we can train these so that they represent probability distributions, so that they all sit within a space that has volume 1, and the volumes are proportional to their marginal and conditional probability distributions. So these are compact models of very rich joint probability distributions. They also represent a kind of representation learning that happens in deep learning. And so they can represent the ability to capture both of these major two fields of machine learning together. So how do we learn these things? Like we do in vector models, they get initialized randomly in space. And then during training, they get moved around by gradient descent according to the training criteria with certain objective functions driven by the data. And once they settle, we can ask questions of the model. Here, this is a simple model that was trained to solve a market basket task. Like if you bought one product, how much might you also like to buy another product, which is of great commercial importance. Here it was applied to movies. And here we can see the purple rectangle represents Forrest Gump. It's a big rectangle because many people like Forrest Gump. The two red rectangles in the upper right are the Lord of the Rings with high overlap with each other. The blue ones are Disney movies with high overlap. And these Hitchcock movies that are more narrow band that come down like this. Hopefully that gives you some intuition. And we find in practice that these models can outperform the state of the art on various tasks of commercial importance. The bilinear vector model has been the standard one in the industry for quite some time. The cone one is another new one, and our model is outperforming both of them. So I hope I've given you a useful little vignette about how to take people from a situation like this into a situation that hopefully looks like this. We've been very happy working on data in biomedicine and in material science and various other areas that are of importance to the state of Massachusetts with various industrial partners across the state. And we'd be eager to talk with additional companies that, that would like to speak with us. With that, I'll close, and thank you very much.
Okay, Andrew, thank you so much. That was really exciting. Maybe you can stop sharing your screen.
Yes, thank you.
I think what we're going to do, it's the end of the session, and what I'd like to do is just announce the Q&A session and invite members of the audience to join us all there. And then the keynote session will go off on its regular schedule. Okay. So let me just make a few closing remarks to close out the session and explain a bit about the Q&A session. So I do want to point out that all of the recordings of today's talks, including Andrew's, will be made available right after, or tonight after this event is over. So look into your email for information about how to access that video archive. I also want to note that we are going to be sending out a feedback survey to attendees at the end of the day, and we'd really appreciate it if people would, if you all fill in that survey, because it helps us improve future events like this one. Regarding the optional Q&A session, so as soon as we wrap up, as soon as I close out now, this session will remain up and live. And we're going to start the keynote session at 3:45 p.m. So about 9 or 10 minutes from now. For those who would like to follow up with any of today's speakers, Andrew, Hamed, Marco, and others, whether they were able to answer questions or not, we've put into the Zoom chat a link to an entirely separate Zoom meeting. So we're going to ask you, if you want to have a chance to chat with any of the faculty from today, just join that Zoom meeting. Just click on the link, say you're going to leave this webinar and join the Zoom session. And then if you do that, just use your original personal Zoom link to come back to this webinar at 3:45 to see the keynote. If you go into the Q&A session and you get you're having a great conversation, don't worry, you don't have to rush right back. Everything's being recorded, so even if you miss a little bit of the 3:45 start of the keynote, you'll still be able to catch it all later, okay? So, and for those of you who are not going to join the Q&A, you can hang out here. We're just going to run a quiet video until we restart at 3:45, okay? Thank you again so much, and we'll see you back in here at 3:45 for the closing keynote.